Chapter 17, Diffusion and Exchange of Gases, which again is kind of the preparation for introducing how gases are transported in the blood. And so we're going to build up the conversation by looking at the partial pressure of our gases and how we deduce the gradients that are needed for gas to move in one direction or the other. And so this kind of explains why we see carbon dioxide moving in one direction, so it's moving from our capillaries to the alveoli, out into the atmosphere, and oxygen is moving in the opposite direction, although both of those gases are present in the same mixture of air. And so we really need to look at the individual pressures of those gases, and that's what the partial pressure is. So that's what we'll be discussing here today. So we're starting off with an overview, basically just describing how these gases move through our vasculature. So they diffuse across the alveolus from the atmosphere, and then they diffuse into, they move into the alveolus, right? According to those bulk flow principles, they diffuse across the respiratory membrane here. So from alveolus to the capillaries that are lining those alveoli, and then they move through our vasculature, and then they diffuse into our capillaries at the levels of the tissues. And so what we really want to point out and illustrate here is that the rate at which oxygen is moving across our alveolus into capillaries, the rate at which this diffusion is taking place is the exact rate at which it is being consumed by our cells. And this is why, for the most part, the amount of oxygen and CO2, we'll talk about in a minute, is same as well, that's present in our arteries is pretty much constant. Okay, because as our tissues and cells are using up that oxygen, that influences the rate at which it is being diffused across the alveolus and into the capillaries. And the same thing is true for CO2, although it's moving in the opposite direction. The rate at which our tissues are producing this gas, producing this byproduct from cellular respiration is the exact same rate at which it is being diffused in the opposite direction. So across our capillaries, back into the alveolus so that it can be expelled into the atmosphere, all right? And so this is why the levels, again, of these gases are relatively constant throughout the vasculature, because that rate of consumption and production is being matched by diffusion. The second thing we want to point out or introduce here is what's called the respiratory quotient. And this is really the rate of CO2 production per oxygen consumption. And so it basically is telling the story of how well CO2 is being produced in terms of matching oxygen being consumed. And so the way that we calculate that is simply dividing our CO2 rate by our oxygen consumption rate. And so if we were to look at this at the level of the tissues here and divide 200, which is the amount of CO2 produced, by 250, the amount of oxygen produced, we would get our standard respiratory quotient, which is 0.8. Okay, so 200 divided by 250 is our standard respiratory quotient at rest. And that can change depending on things like our diet. If you're having a lot of fats in your diet, your respiratory quotient can go down. If you're an athlete, if you're very athletic, you can have a higher respiratory quotient, and that can change depending on our physiologic state and so on. All right, so that's kind of just an overview about how the rate of oxygen consumption and CO2 consumption are kind of related to each other. Let's talk about our first objective here, which is to understand some of the physical factors that affect the diffusion of gases into and out of our bodies. And so we talk about this diffusion taking place across our respiratory membrane. And remember, our respiratory membrane, just to remind ourselves here, is the alveolar type 1 cell fused with the basement membrane of the endothelial cell. And so that is that very small membrane, or thin membrane rather, which facilitates gas exchange. Now we can also introduce some of the factors that affect how well diffusion takes place. And that's going to be the partial pressure of gases and then the solubility of gases. So we'll speak about these two factors individually in a little bit more detail, but to just introduce this idea of the partial pressure of a gas, it's basically the individual pressures of a gas mixture. So when we think about air that we breathe in, it's not just oxygen. It's got nitrogen in it. It's got a little bit of helium. It's got CO2. And so the pressure of that overall gas, when we spoke about, for example, 760 being our atmospheric pressure, that is a combined pressure. So that is a pressure that is taking into account the pressure of oxygen, the pressure of nitrogen, the pressure of CO2. And so this is where we get this idea of partial pressure from. And the individual partial pressures will then influence how these gases are moving individually. We also want to remind ourselves of the ideal gas law, right? This PV equals nRT. And so the relationship here is that the pressure of a gas, which we're going to speak at length about coming up, is dependent upon the temperature, which for the most part in our physiology is standard, the number of gas molecules, which is definitely moving and changing, and then the volume of the container, which we talked about really being that thoracic cavity. And so we're actually going to recall this relationship and speak about how it applies to these individual partial pressures of our gases. Okay. So moving on here to kind of continue that conversation, we think about air that we breathe in as a gas mixture. And so the mixture of gas is having several different gas molecules making up that entire mixture. And so in order to think about the overall pressure of a gas mixture, we want to think about the proportion of the pressure that's due to the presence of individual gases. In other words, again, thinking about our air that we breathe in, having several different gas molecules present, we need to look at the individual pressures of each of those gases in terms of finding out the total pressure of that gas as a mixture. And so the equation to do that here is the pressure of the total gas mixture is equal to the pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas, and so on until we get to the very last gas, which is N being how many ever number of gases are present in this gas mixture. And that is how we deduce the pressure of any type of gas mixture. And so this is how we got that 760 being our atmospheric pressure, specifically at sea level. We simply add or sum the total of the individual partial pressures of all the gas molecules that are present. Now, how do we find the partial pressure of an individual gas, right? How do we find this P1, P2, P3? We simply multiply the percentage of that gas by the total pressure of the mixture, okay? So for example, if we're thinking about the partial pressure of oxygen, we're going to think about the percentage of the entire mixture that's made of oxygen. So we'll talk about oxygen being about 79%. And so we multiply that 79% by that 760, which is the total pressure of the gas mixture itself. Okay, and we'll apply this coming up. So don't be worried, just make sure you understand this equation in terms of calculating the partial pressure of an individual gas. Okay, so to apply that here a little bit, we're thinking about our composition of air. And as I mentioned before, air is made of several different gas molecules. It's 79% nitrogen. It's 21% oxygen. It's got some trace amount of carbon dioxide, helium, argon, and a few other gases that we don't really have to worry about. And so we think about water as well. So water also has its own partial pressure. And we'll talk about coming up that we need to take into account the partial pressure of water when we think about humidified air or air that has additional moisture to it, which becomes really important as we think about the conducting zone. So the conducting zone adds some moisture to our air, and by extension, it's actually going to change the composition of air because we have to account for the partial pressure of water as well. And so let's think about dry air here first. So we're thinking about the total pressure of dry air, and that is at sea level, 760 millimeters of mercury, right? If you remember this number being our absolute atmospheric pressure at sea level. And so what that is a combination of the partial pressure of nitrogen mainly and the partial pressure of oxygen mainly. And we're going to kind of ignore some of the trace amounts of other gases. So calculating the partial pressure of nitrogen, we simply multiply the percent of our total mixture that is nitrogen. So nitrogen is 79%, so 0.79 times the total pressure of our mixture, which is 760 millimeters of mercury. And so the individual partial pressure of nitrogen is 600 millimeters of mercury. All right, hope everyone is staying with me so far. And we do the same thing for oxygen. So oxygen is 21% of our air, right, of that entire gas mixture. So we multiply 0.21 times our entire pressure for the mixture, and that is 160 millimeters of mercury. Now, air is very, very, very small. Air is a small amount of carbon dioxide, or rather, carbon dioxide is a small amount or a small percentage of air. And so it is a very minimal amount. But if we were to calculate this, it would be 0.03% times, again, our 760, and that would be about 21 millimeters of mercury. So very, very minimal amount that we can kind of ignore altogether. Now, as I mentioned earlier, at 100% humidity, we have to think about water and its effect as a gas on the composition of our air mixture. Water has its own partial pressure, which is 47 millimeters of mercury. And so again, when we think about that dead space, think about that conducting zone where moisture is added to our air, it's no longer just the partial pressure of our gases, but we want to add now the partial pressure of water because it completely changes the composition of air. And so if we were to recalculate that total pressure, right, the total pressure of 760, we now add the partial pressure of water, which is 47 millimeters of mercury. And so we'll see that the other partial pressures are now decreased because they're a proportion of our total gas mixture. So whereas in dry air, the partial pressure of nitrogen was 600, if the air is humidified, it's going to be decreased to 563 millimeters of mercury. Okay, same thing for oxygen. Whereas in dry air, the partial pressure of oxygen was 160. In humidified air, now that we've taken that 47 millimeters of mercury into account, it is slightly reduced to 149 millimeters of mercury. Okay. And so just adding up these numbers here, we should get our total combined pressure, which is 760. And this is true for any gas that we would add to that air. Any type of gas that we add to the air, we need to now take account of that in terms of the partial pressure that it will contribute to the entire gas mixture. All right, so that was all about the partial pressure, and that has a great deal to do with how these gases move in different directions throughout our vasculature and across the alveolus. What we're going to speak about now is the solubility of gases. And the solubility is basically how easily do these gases dissolve into a liquid, and more important for what we're discussing here for our purposes, how easily do these gases dissolve into our blood? Okay, so a gas can exist in two forms. It can exist in its gas or its vaporized form, and then it can exist in its liquid or its dissolved state. And so the ability of a gas to dissolve depends on the properties of the gas as well as the liquid. We basically have to think about the partial pressure of the gas in the vaporized state and the partial pressure of the gas in the dissolved state. And after that gas has dissolved into that liquid solution, we now see that the partial pressure of the vaporized state and the partial pressure of the dissolved or the liquid state are at equilibrium. Okay, I'll say that again. After we expose, let's say, a liquid with no gas in it to some type of gas, and that gas has now dissolved into the liquid, those two partial pressures are now at equilibrium. In other words, the partial pressure of the gas in its vaporized state, so its air state, and the partial pressure of the gas in its dissolved or liquid state should be at equilibrium after that gas has dissolved into the liquid solution, right? The second thing we want to speak about is called Henry's law, okay? And kind of stick with me here. This may be a little bit confusing, but we're going to clarify this and talk about why it's important to talk about these things. But Henry's law is really the the molar concentration, in other words, the number of dissolved gas particles, is equal to Henry's law constant, represented by this small k, multiplied by the partial pressure of a gas in the atmosphere. And the important relationship of Henry's law is the directly proportional relation between the number of gas particles and the partial pressure of the gas. In other words, if I increase the number of oxygen molecules that's present, I'm going to increase the partial pressure of oxygen that is being dissolved, okay? And so there's that directly proportional relationship. The opposite is true. If I decrease the partial pressure of the gas, then I'm going to decrease the number of gas molecules that can then dissolve into a solution. All right. I'm going to pause here and see what questions we have so far. Okay, so now this brings us to speaking about oxygen and carbon dioxide and their differing solubilities. So all that we've just said is really to hone in, to drive home this idea that oxygen and carbon dioxide have very different solubilities. And we'll talk about why that's important in a bit as well. So at 100 millimeters of mercury, partial pressure in water, oxygen is going to dissociate to 0.15 millimoles per liter. In other words, 0.15 gas particles, whereas CO2 is going to dissolve to 2 times that amount. It's going to dissolve to 3.0 millimoles per liter. And what that really describes or highlights is that CO2 or carbon dioxide is much, much more soluble in water and for our purposes in blood than oxygen is, okay? I'll say that again. Carbon dioxide is much more soluble. It's going to dissolve much more easily. It's going to travel and move around much more easily in our blood than oxygen does. Okay, because it's much more soluble than oxygen is. Let's see. Is it the concentration of dissolved gas and the partial pressure that is directly proportional? Yes, that is true. So the concentration of the dissolved gas or the number of gas particles is directly proportional to the partial pressure of that gas. Okay, and that was what Henry's law kind of described. Okay, so yeah, just making this point that CO2 moves around much easier in the blood. And this is the whole reason, kind of a backstory, this is the whole reason that we need hemoglobin, that we need these erythrocytes with hemoglobin, because oxygen does not move around very well in our blood. It needs that chauffeur that we spoke about. It needs some type of molecule to kind of grab it on, grab it or latch it onto that molecule, and then it can move it around in the blood, because unlike CO2, it does not solubilize, it does not dissolve and move around very nicely in our blood, okay? Although CO2 can bind to hemoglobin to a very small extent, most of our CO2 can dissolve quite nicely in our blood. It can dissociate into some other things that we talked about, such as carbonic acid, and move around in the blood, whereas oxygen needs that hemoglobin in order to do so. Okay, so this illustration is just further highlighting that idea, further highlighting that point. So on the left here, we've got a beaker. It's got water in it. So this is pure water, right? We're presuming that there's no oxygen dissolved in this water just yet, but it is being exposed to air where we do have vaporized oxygen molecules, okay? And the partial pressure of oxygen in this air is 100 millimeters of mercury. And so we expose this water to air and allow it to sit for some time such that it's allowed to equilibrate or to reach equilibrium. And after after that air has dissolved into that water, we now see that the partial pressure of the air in the vaporized state and the partial pressure of the air in the liquid or dissolved state is now at equilibrium. They're now the exact same. But if we look at the number of gas molecules that we have, we see that we don't get the full amount of these gas particles dissolved into the water state. And what that tells us, or what that further illustrates or proves, is that oxygen does not dissolve very nicely in water, right? We only have 0.15 millimoles of oxygen in terms of the liquid or dissolved gas molecules, whereas in the vaporized form, we had 5.2 millimoles per liter, okay? Another way to express this idea is that if we had a completely soluble gas, if we had, this ideal perfectly soluble gas and we allowed time for it to equilibrate with a liquid solution, we would see 5.2 millimoles of this gas in the liquid form, just like we see 5.2 millimoles of this gas in the vaporized form. Okay, but if we think about oxygen, it is not very soluble at all. And so most of that gas does not dissolve. Only a very small amount of that dissolves into its liquid or dissolved state in this solution. All right, and then we can compare that to carbon dioxide here on this slide. So once again, we have our water exposed in this beaker to carbon dioxide to start, and we allow time for dissolving to happen and for these two partial pressures to become at equilibrium. And when they do, right, which you can see here, the partial pressure in the vaporized state is 100 millimeters of mercury. The partial pressure in the liquid state is also 100 millimeters of mercury. When we look at the actual number of gas particles that are dissolved in this solution, it's not perfect, so it's not 5.2, but it's much better than we saw for oxygen. It's actually 2 times better than what we saw for oxygen. So instead of having 0.15 millimoles of this carbon dioxide in the liquid state, it's actually 3.0 millimoles that has been dissolved into the liquid state here. And so just these two illustrations just further highlight or further prove that carbon dioxide is much more soluble. It dissolves better, it moves around better in water, and more importantly, in our blood than oxygen does. Okay. So I just really want to kind of simplify all that we just said and put it into context. The whole reason that we talked about that and the different solubilities is really to prepare us for speaking about hemoglobin that we'll look at in our next packet. This is why we need hemoglobin, in order to chauffeur that oxygen around, because it does not dissolve easily as we see with carbon dioxide.